Thanks so much for attending today. So our speaker is Dr. Sanlyn Buxner. She, as you can see, she works for the University of Arizona and the Planetary Science Institute. I first encountered her when we together worked on a book. We worked on a book that compiled the proceedings of a conference in science education and outreach. And ever since that time, I thought, man, what a fantastic resource and what an opportunity it would be if she could come here to Salt Lake Community College and talk to us. And this symposium turned out to be the perfect venue for that. And so I'm very grateful that she decided to come. She's an assistant research professor in science education at the University of Arizona and a research scientist and educational specialist at the Planetary Science Institute. She has worked in space science education and public outreach since 1996. Over the last 20 years, she has worked in formal and informal education in science museums, outdoor schools, and universities. Previously, she worked as the education and public outreach specialist for the Mars Odyssey Gamma Ray Spectrometer and NASA's Phoenix Mars Lander. She currently works on several NASA-funded projects working with scientists, teachers, and children. Her current research interests include examining issues related to scientific literacy, how to measure it, and investigating how it is changed by education outreach and online media. Additionally, she investigates how science research experiences can be used to improve both science understanding and empowerment of teachers and students. I asked her earlier, she spent a little bit of time at the planetarium and at the University of Utah, but other than that, this is her first visit to this part of the valley in Salt Lake Community College, and I'm so excited to introduce Dr. Sanlyn Buxner. Thanks.
Well, good morning, and thank you for having me. I had a lovely flight up from Tucson, and you have wonderful weather. I'm happy to tell you it's much cooler here during the day than when I left Tucson. I'm going to talk a little bit about my trajectory. Lots of people always say, how do I become you? And I was a very non-traditional student. I started traditional, and then I kind of fell off. And so I want to talk, but if you have questions as we go, just ask. Like, that's way better than having me just go on and on and on, right? I'd much rather have a dialogue with you. I'm going to talk a little bit about some Mars work and my life, but I want to know a little bit about you. And so I do work at the University of Arizona and the Planetary Science Institute. And so I'm not a traditional faculty member. I work at the university part-time, and then I work at a nonprofit. And the Planetary Science Institute's a really interesting place. All we do is research. We don't teach. Right? So we're a group of scientists, I have students, I have research assistants, and we just kind of explore stuff in the solar system. It is a soft money institution, which means we have to write grants or get gifts, endowments, but it is one thing I want to talk about as you're thinking about where you might want to go. Institutes like that actually exist. And I'm going to introduce you to a lot of the students I work with, but I employ students through this institute, so we get NASA funding and National Science Foundation funding, and even some eccentric, wealthier individuals, right, who like to do cool stuff. So we'll talk about that. But I want to know a little bit about all of you in the room. And so just by a show of hands, how many of you are currently a STEM major somewhere? Okay, half. How many of you are currently not a STEM major, but you're thinking about it? Okay, no to target, good. How many of you not a STEM major, but you thought, science is kind of cool, I might want to do something like that, even though I don't want to be a scientist or an engineer? Okay. Anyone interested in education, being a teacher? Okay. So that leaves the rest of you, other than you got bribed to come here, right? So start shouting out some things about you that we haven't talked about. Awesome. Medical profession. That's perfect. What else? Exercise scientist and awesome, software engineering. I totally, just by the way, put software engineering, my husband's a software engineer, into the STEM field. And so, we always talk about this acronym, science, technology, engineering, and math. That encompasses so much stuff, right? And we'll talk a lot about that. What else? The rest of you I'll put into consumers of science for now until you tell me more about yourself. Okay, so we all are consumers. You have your cell phones, lots of technology there, all the things. But talk a little bit of this. I'm going to talk a little bit about me. And so these are the titles, right? We all have our titles. And so I'm an assistant research professor. That's a really fancy way of saying I have to write a lot of grants and do a lot of research and publish stuff. So if you're thinking, hey, being a professor is really cool, right? We can talk about that. In a traditional professor, you have lots of faculty here, right? There are kind of 3 components to being a professor, if no one ever told you, right? You have to do research most places. Now, you might get lucky and go to a teaching school, and then it's teaching. You always have to teach. And then you have a service component. And so as you're looking for your faculty jobs, right, kind of balance your service, your teaching, and your research, and kind of go, which of those do I like more? Do I want to go to a research school, a teaching school, a service school, right? But that's kind of what that's all about. So mine, by my title, I do research. So I am not required to teach. So I get to teach anything I want. Kind of cool. But I do have to write a lot of grants. Not as cool, right? So you kind of think about that. I am a research scientist, and I do a lot of research. I'll tell you a little bit about my research at the end. I do a lot of social science research now. So I actually study lots of rooms of people like this. So I'll tell you a little bit about that. And then I'm an education and communications specialist. And that just means that I do a lot of things related to talking about science and STEM, things like that. So those are my titles, right? But that's not the only thing, right? I am also a parent and a spouse and a child and a caretaker. And I suspect that is true for many of you, that you have a lot of other obligations besides going to school and working. And so I think it's really important when you think about your trajectory, and this is always something I think about as well, is how what I'm doing is going to impact the rest of my life. This actually is my daughter, and we had the great fortune to go to the launch of the OSIRIS-REx mission, which is going to an asteroid, and we were there in September. And so she looks really happy there, but it was really hot. It was in Florida, and she was kind of miserable. It was really a humid day. And then I'm also a volunteer, I'm an advisor, and I'm an advocate. So again, as you're thinking about these STEM parts of your life, I always think about how all of that goes together, right, to make what I do every day. So how did I get where I am? Well, I'm going to tell you a story about where I went to graduate school, and in the process, we're going to have you do some stuff with me. And so when I went to graduate school at the University of Arizona, I had the great fortune to get a research assistantship. And so for those of you thinking out there and saying, wow, how does this all work? Often in our STEM fields, like science, engineering, and math, and technology as well, you get an RA. So what does that mean? That means somebody pays for you to go to school. That's pretty important, right? School's really expensive. And so, if you look at a PhD, it could cost you $100,000 out of your pocket, which 99% of us do not have lying around. And so how do I do this? Well, I decide I want to do research. I'm going to go ahead and get a research assistantship. Sometimes they exist for masters, not as often. Very often they exist for a PhD. So I just happened to stumble at the University of Arizona into an RA where I got paid by several Mars missions. Cool, right? Super, super awesome. So I learned a ton about Mars while I was in graduate school, and we're going to talk a little bit about it because I want to talk about this story of Mars exploration. And so this is where you are going to ask you to do some work. So the first picture over here is a picture of Mars, which it's the red planet, right? Fourth planet from the sun. And the white region right here, let's see, oh good, it's working. It doesn't move around from day to day. And it might look really familiar to you, right? You have something kind of like it around here. But it does increase in size in the winter, and it decreases in size in the summer. You guys are in a snowy place, right? Seems kind of familiar. Okay, so as a scientist, as all the scientists here, what we want to ask ourselves is, what is happening? And then we want to ask, why? So what's happening? In the winter, that white thing grows, and in the summer, it shrinks. What's going on? Possibly snow. Other explanations? We could have water, we could have liquid, we could have some water, we could have ice. What else? Any other explanations? You gotta be really creative, right? Salt. Could be salt, absolutely. What else? Yeah, it could be CO2 ice. What else? Yeah, it could be storms, right? These are all the explanations of things that we go, if you are studying the Earth, you're around here on Earth, you go, let's think of all the reasonable things it could be, right? But the more important question is, we have this question about this planet that's quite far away, right? By the way, no human has ever been to Mars, so we haven't actually been on the ground to check it out. So here's the most important question. How do we find out what's going on? Satellites. And what do satellites do? They get us information, yeah. Okay, so first, right, we want to make sure everybody's on the same page. Where do satellites hang out? In orbit. And that's really important, right? It's really important to know that satellites are in orbit. Now, we can take pictures from Earth, right? We have telescopes, and some of you may have been able to look at Mars through telescopes, and you'll know it's this little wispy dot. And if you're really lucky, on a good, right, with good seeing, you can see maybe a white thing on there. And you go, right? So we need to get into orbit for lots of reasons, right? And we have lots of satellites in orbit. And in fact, we have satellites in orbit around Earth, and we have satellites in orbit around Mars. And we're going to use both of those to try and answer this question. So you gave me the first piece. I need to get some more pictures, right? Of what? I want to look at the white spot. What else do I want to look at? I might want to look at the atmosphere. Great. Yeah. Yeah, I want to look at the geography, the topography, all things like that. Now, I have to focus in, right? And I have to go, my question right now, there's a lot of cool stuff about Mars. My question right now is about that white spot on the northern hemisphere. So I'm going to use some tools. So those of you who have had the luxury to take your physics and astronomy classes might recognize, this is from high school as well, right? We have lots of different types of light. Right? They call it the electromagnetic spectrum. And the really interesting thing about this, since no person has actually stepped on Mars, is that these are tools, right? This light, collecting this light, are tools to helping us understand all about things that are far away. And so the interesting thing about astronomy and planetary science is we don't get to go there. It's not really a lab science so much as a waiting for the history to come to us. And today I'm going to tell you a story about 3 kinds of light on 3 different satellites that we were able to put together to do this. The first, you know all about, it's visible light. It's that stuff reflecting off of all of us, going into our eyes so we can see. Okay, cool. The next one is infrared. What do you guys know about infrared? Yeah, it's a great heat signature. That's a really great shorthand on infrared. Okay, so we're going to show you some heat maps of Mars. Now, why is that important? Why would I want a heat map of Mars? Yeah, so some of you said it might be ice, so that might tell me about ice, right? Tell me about all sorts of things, like seasons. And it might go, well, right, the one thing we didn't say, we said in the winter, right, we have to think about how we define winter, it gets bigger, but we didn't say when it gets colder it gets bigger, we just said in the winter. So maybe that's something we want to investigate. Are those things actually correlated, right? Because, right, winter could be defined different ways here. Okay, and then there's one other kind of light, which is this really weird stuff way over on the high end of the spectrum called gamma rays. You guys know anything about gamma rays? We don't have a lot of experience with gamma rays. Yeah, super high energy. Say that one more time. Yes, awesome. Penetrates the surface, really good. Anything else you know about gamma rays? All right. We kind of see them around nuclear power plants, things like that. But like I said, we don't have a lot of experience. Our wonderful atmosphere protects us from all of those gamma rays coming in from the sun. Good news, so you can already think about why we need to be in orbit. Okay, so we're going to use these 3 kinds of light. They are not the only answer. They're just how we did it. Okay. Now, you actually brought a really good point, because one of the most important things to know about these light is how deep can they go into the surface. Visible light, surface, right? I cannot use any visible light to look inside and see anything else about you except for what's on the surface. And that's important to remember about Mars. When I'm looking at those Hubble pictures that I'll show you in a second, I can only see what's right at the surface. When I look at infrared, I can get an entire millimeter down. Cool, right? But that's that temperature piece. But the really key piece to this was that we were able to use gamma rays to go 10 to 50 centimeters, right? That's pretty substantial considering no shovel with a human has been on Mars. And when we were doing this work, that was true, right? This, by the way, was done before some of you were born. Probably a lot of you were born, so I'm just going to tell you this. It's still really cool stuff, right? Done in the 90s. Okay. Here's something else. Now, we can use some lab work to help us understand this. So maybe we had some questions about ice. Now, we already know it's white. We saw that. And so we could go into the lab and take some measurements about the ice. And I put 4 up here for illustrative purposes. So we could say it's water, carbon dioxide, ammonia, or methane. Those are all actually really common in the solar system, so those are perfectly reasonable ideas, right? It's always good. You can see their visible brightnesses. They're all bright. That's good. What we're looking at is bright, right? And then we're going to look at the Martian frost point temperature. So it's kind of important we understand what that means. What do we think a frost point temperature is? In just everyday language, what is that? So it's close. It's not just how cold it is, it's a specific point. Yeah, so it's where it becomes a solid, where it freezes into ice. Now, it's really interesting. If you've ever studied Mars, you know the atmosphere is about 1/100th the atmospheric pressure on Earth, right? So water doesn't really get into a liquid phase. It sublimates straight into a gas. So this tells us, right, where we might expect to see the point of frozen stuff. So we're going to put all 3 pieces together. I know I'm making you put all this together, but I want to know how far down can I see and what are the temperatures, right? I'll bring these back when we look at our data, but I just want to put that out there. With these pieces of information, we're now going to build a story of what is going on that white piece of Mars. Okay, so let's do this. So you guys told me all about these satellites. So we call this type of science remote sensing. It's because I'm not there, right? I'm not in situ, I'm remotely sensing it. So this, one of our very favorite satellites in orbit around the Earth, the Hubble Space Telescope, which will be very soon replaced by James Webb in just a couple years. This has been a workhorse and a wonderful legacy. This is where our visible pictures are going to come from. Okay, so these pictures came from a satellite going around Earth, a really great satellite. Okie dokie. We have Mars Global Surveyor, which went up in 1996. This one, we had to get all the way to Mars. So just think about some of the technological feats of doing that, right? It's not just in orbit around here. We had to get it to Mars into orbit. So it was going around Mars, taking some pictures. And then this one right here is the one that I got paid to work on when I was in graduate school. And this is Mars Odyssey. It was a 2001 launch. And the instrument that I worked for looks like a toilet. It's right here. Yeah. And that is what collects gamma rays. Now, it's important to know we do not shoot gamma rays down into the surface, right? They are actually naturally occurring as the sun radiation hits. We also have some radioactive processes. And so we are, again, passively collecting this light from orbit. So we haven't even gotten there. We're just taking pictures. So let's see what those pictures tell us. Here are the visible pictures. Okay, so there are no, like these weird pie things are just missing data. These are mosaics, right? So they're putting stuff together. And so these are pictures from the Hubble Space Telescope, looking down at the northern, right, the northern pole, and you can see northern winter, northern summer. It was just as I suggested, right? It gets bigger and it gets smaller, right? Now, based off that, what can you tell me, right? You can tell me pretty much what we said before. Something is growing, something is shrinking. Do you have a feel for what it might be based off of this new and enhanced picture you have? Yeah, absolutely.
So did you say that there's no water phase, so it's either ice or gas?
Correct. Yeah. So what can you tell me about this? Like, what can you conclusively go and put on your poster to present to all of your peers and you feel good about? Yeah, something's growing, maybe freezing, but that might be my inference. But yes, something's growing and shrinking, and it's bright. And if I think it's ice, let's just pretend for a second I think it's ice. Of my 4 choices, right, water, carbon dioxide, ammonia, and methane, Can you tell the difference by how bright it is? No way. They all said bright. This is bright. Can't tell. And that's a really important point, right? You can only use the evidence you have at hand, right, to make this conclusion. Okay, cool. So we had this picture. We went, let's get some more data. I already gave you the precursor. So remember, we're going to move to our friend, the infrared. Here are infrared pictures. I need to use the word picture very carefully. This is not a picture. This is a data representation, right? So can't actually look at Mars and see that. And there's a key, and I apologize, the key is like microscopic, so I'm just going to give you the end of it. Again, we have put winter on the left, right? Summer on the right. The bluish stuff is colder. The red and yellow is warmer. And I can start to give you some, let's see, it's pretty important. The blue is right here around 120. Negative 120 degrees Celsius. So we can look at our chart in a second. And when we start to look at yellow, yellow's up here in the kind of 60 degree-ish. Okay, so I have temperature. How are you feeling about temperature now? What have you learned that you did not know before? It's colder, and you go, amazing, it's colder, right? Cool, winter, it's colder. What else? Right? So he says can't be ammonia or methane because it's not cold enough. It's not cold enough. So if we look at the chart, right? If you look at that frost point minus 200, minus 220, and we go back and we go, nope, bottom of the range is 160. So good news. Good news, I can cross them off. Now I've got it down to 2. I've got it down to water, and I've got it down to carbon dioxide. Let's look at the temperature really quick and make sure that that actually works, right? Minus 123, minus 75. So when I look at the temperature, this is the important point. In the winter, when I said it's like minus 120, what could it be? It could be carbon dioxide. Could it be water? Absolutely. It could be really cold water frozen there. And that's important, right, to know that. Okay. Can I tell the difference between the two? No? Now, what about, here's a good one, right? Well, we'll get there. But, so here's my temperature. So I go, well, I kind of got it down, but that's not enough for me. Okay? So I'm going to add in the third piece of data. This is my gamma ray data. So remember, gamma rays get a little bit down, and they're telling me something actually about the elements I see in the first little bit of soil or ice, whatever's there. Okay? So again, winter over here, summer over here. What do I see? Well, this is in relative hydrogen signal strength. It's important. If we remember what water is made out of, it's made out of hydrogen. That's probably the most important piece here. And so when I take a look and I go, okay. By the way, blue on this one, is 0. 0 hydrogen, okay? And over here, when I look at my relative hydrogen signal strength, I see about 50. And this is where you squeak your head and go, can you tell me a story of what's going on? So to review, and then we'll talk about it, right? We have 3 pieces now. We have, well, the visible, something's growing, shrinking, possibly ice, definitely colder, kind of like where carbon dioxide could be, here. Could be carbon dioxide and water here. Could it be carbon dioxide? Why not? It's too hot. And carbon dioxide also sublimates, right? Yep. And then here's my last piece. Okay, I see 0 hydrogen. I see some hydrogen. So at this point, I want you to turn to your neighbor, because maybe you have no idea what just happened, and that's okay, right? This is not something that we actually did in 15 minutes. We actually took a long time. And describe to me a story of what you think is happening based off of this. Because now you've listened to me for a good amount of time, so you should try talking and stretching. Okay. Does someone want to tell us a story? Awesome. Someone want us to tell us a story of what they think is going on? Okay, someone, so you got the data, you're ready to go to the conference and say, this is what's going on. Do you want to try? So this is what he said. He said, in the winter, we see a lot of CO2 that is probably covering up the water that is there. And then when it gets too warm in the summer, right, it sublimates and that water is exposed. And that is, in fact, what we see. It's a really cool story. So this is not like the Earth, right? There is 95% carbon dioxide in the atmosphere. Interestingly enough, when it gets cold enough in the winter, it gets really thick on that pole and it covers it up. In the summertime, warms up. Guess where all that carbon dioxide goes? What do you guys think? Goes in the atmosphere, but interestingly enough, it actually goes to the other pole. And we can watch this. The South Pole's a little weird, but we are watching carbon dioxide go back and forth. Now, right, here's sometimes when I do this, I actually do this exercise with my students, and some of the explanations that I get, right, I want you to think about, right, so sometimes people tell me, well, clearly the water melts. That's why it's gone away. Yeah, you should have a funny look on your face, right? And you go, well, no, it's certainly not warm enough for that to happen, but you can start to think about how we put these pieces together when you say, what are all the possible explanations? I'm going to keep going in my story, but this is, like I said, one piece that I like to talk about where we're using all this data together. And using all this data, we were actually able, with this instrument, with the Gamma ray spectrometer, to make global maps of elements on Mars. And that's really, really important. It's important for us to understand the geologic history, and it's important for us to understand the history of water. This is near and dear to my heart. This is a global map of relative hydrogen, which is a proxy for water or hydrated minerals all over the planet. And you can see that near the poles it's really high, and near the middle of the planet is relatively low. This data allowed a group that I later joined to go back to NASA and ask for about $400 million to send a spacecraft to land on Mars. And so that was the second half of my graduate career. I got to join that. But it was this really awesome thing where I had worked on an instrument that had mapped the water on Mars, and then they asked for money from NASA and said, we think it's there. Right? We see evidence, but we've never touched it, and we want to touch it. We're going to build a robot, and we're going to touch water on Mars. And so this was the mission that was proposed and selected as part of the Scout missions that NASA did. It was the Phoenix Mars lander, and it was really interesting. It was run out of the University of Arizona. Very unusual. A lot of missions are run out of NASA centers. This was run out of the University of Arizona, which means we had so many students that worked on this mission. We had undergraduate and graduate students, and they got paid to do this. So if you're thinking that's cool, it is really cool. And I'll show you some of the things we got to do. And so what we got to do was study the history of water in the Martian Arctic, right? And it was and still is the farthest north we ever landed a spacecraft. This is what it actually looks like, the real thing. So it's kind of like 3 dinner tables next to each other, and these are solar panels, and that's the main part. And I'm just going to show you really quick, because I think EDLs are really cool. This is the landing animation. I show this to you for several reasons. So here it is coming to Mars. I didn't show you the launch, but it's traveled for about 8 months, and it comes into the Martian atmosphere, very thin atmosphere. And so it's going to hit the atmosphere at about 13,000 miles per hour. Now I want you to think about this. This is an animation that someone made. There was no CNN crew, right, at Mars, although lots of people think there were. Okay, the parachute comes out. That parachute has to get it from thousands of miles an hour to maybe 1,000 to hundreds of miles per hour. It really has to slow it down. So you can think about all the engineering that goes into this. We have to test it on Earth. The spacecraft came out. It did have a landing camera at that point, and then it dropped, and it had retro rockets. Now, all those retro rockets had to work. If they did not, we would reach the crash site very quickly. There it is, and it landed. So think about all the things that are going on right now. I'll let it play for a second. Something that's really important to understand is that this is not real-time navigation, right? Mars is anywhere from 4 to 20 minutes away when we're able to communicate with it, depending on where we are in the sun. So this all had to be onboard programming. So those of you who are talking about being programmers, software, we need so many software engineers to do work like this. Saw all of the solar panels deploy, we had cameras, and then the main workhorse of this specific robot was this robotic arm. So we wanted to dig down where those gamma rays could see and actually see. You can see again in this animation, you see a lot of dirt, not so much ice. And so this was the Phoenix lander, and we landed in 2008, and I'll just show you some of the highlights from that. There we go. Oh. And so like I said, very far north, about 68 degrees north latitude. And this is a real picture now. So this one we actually took a real picture. You can see the robotic arm. And the really interesting thing, I live in Arizona, this looks like my backyard, right? It's really, I go, wow, that looks like the desert. Mars is so Earth-like in a lot of ways, and we're very excited. Here's the other cool thing I want to tell you about. This is an engineering marvel. This is a picture, a real picture of our spacecraft entering the Martian atmosphere. Now remember, there was no CNN crew or any other crew. How did we capture this real picture? What do you guys think? How do we capture it? Here it is, by the way. There it is on the parachute. How do we capture it? We had a satellite. It was not from Earth. We had a satellite going around Mars. And if you want to think, if you are into math, the math that was used to collect this. Imagine right now I have something the size of this coming in, landing through the Martian atmosphere, and I have something in orbit, right? Hundreds of miles above Mars. Imagine the math it took to snap that picture. And this is that spacecraft. This is the Mars Reconnaissance Orbiter, which is still a huge workhorse. This camera right here is called Highrise. It's like a telescope looking down on Mars. We run Highrise at the University of Arizona and employ a lot of students in RA. So we have students right now who target with Highrise. And so it does stereo acquisition, and this is the resolution Highrise has. It has a meter per pixel resolution. So this is our campus. You can kind of see if it were looking down on Earth, it could even see your little table blobs here, right? You may not know the exact color of your shirt, but it would know all of you are here. Okay, so this camera, this telescope took that picture. It was incredible. It was the first time Highrise had done it. Now it's kind of like everybody wants their picture taken when they're coming in. But you can see when it landed, you can see the different pieces from Highrise. And so again, we use Highrise for a lot of topography, but it was just such a cool thing that we got. And then here's a real picture of the spacecraft on the surface, again, from orbit. We did get a really up-close look at the soil, and so we were able to take a microscope, take wet lab chemistry, all sorts of neat stuff, and there was a little drill bit on the end. It's called the RASP. This was one of the instruments that I worked for called the TIGA. It was an oven. We were able to bake it, so we're talking about we had a robotic arm, go out, scoop it up, dump it in the oven. This is like the chemical tongue that went, yep, that's water. So we went to a lot of time and effort to actually touch water on Mars. But we did ground truth that water, and that was really an incredible story. You can actually see that frost underneath the soil. Cool, so I did that, and that was really fun, and then I managed to graduate. The Mars program has continued on. I'll just tell you a little bit about it. So Curiosity, which is the Mars Science Laboratory, has been there and is doing incredible work, not at the North Pole, but doing some really neat stuff. But I want to tell you about what's coming up, because you guys are all at the age of maybe getting to work or wanting to work on some of the future Mars missions. I want to tell you a little bit about that. I do want to show you this picture just to give you an idea. This is made by the Planetary Society. This stops in 2013, I think, but it shows you all the things we've sent to Mars. Probably not aware, right? But look at this incredible array of not just American, European, Russian spacecraft. So a lot of stuff going on just on this one planet. Here are the things we've landed on Mars or sometimes crashed on Mars, but that's what's going on. Not a ton, right? And I also like to just show the relative size. I didn't have a lot of time to talk about how we land things, but when we started in 1996, we had little, tiny, that's about the size of a little cart, all the way up to Mars Science Lab is the size of an SUV. So we're getting bigger stuff there, doing a lot of stuff, right? InSight will be going next year, so we'll be launching this next year, actually from California, not too far if you want to take a little drive. It looks a lot like Phoenix because it uses the same body. This one is going to do a lot more seismology work, so it'll have a probe that goes about 15 meters down. But this one I mentioned because it's Mars 2020. So now we're really getting into some time when you might be around to maybe do some stuff. And so Mars 2020 is going to investigate geologic processes, look at habitability, and really think about past life. Okay, so these are the sites. And then the last thing I'll show you about Mars really quickly is just talking about NASA's strategy. So again, this is just one agency. It is the US federal agency of how we're dealing with going to Mars. And so you can see kind of all the stuff that we had done into the future. What are we looking at? And really thinking about early on, we were following the water. We managed to find the water. Now we're looking at habitability. We're going to be looking for signs of life. But really, in the current strategy, under the current administration, we are thinking about how to prepare for human explorers, right? Sending people to Mars. Right? I am not going to be going to Mars, getting too old, right? But start to think about if you want to be a part of that. And then these are the overarching goals that, again, drive our Mars exploration. And this is all part of our portfolio as we think about going to Mars. And then the last thing, if you're into aeronautics, just have to show you something really cool. Armstrong, which is out in California, is also working on these little mini planes that would be deployed. It's called the Prandtl M. They have a Prandtl that they are working on right now that is revolutionary. It's a revolutionary aeronautics design, but they're also looking at deploying many of these to map Mars. So there's just so many cool things in just this one microcosm of science. And so what I want to think about is, when I talked about this, I was trying to show you animations and pictures and all this to think about all the jobs that might be related. So if you're already on your trajectory and you know what you want to do, cool. If you don't, I want to kind of point out all the ways that we pay people to work just right in what I showed you, right? So it's clear that we have scientists. We have lots of scientists that work on projects like this. You can be an astronomer, you can be a biologist, a planetary scientist, a geologist, lots of different things. We need so many engineers, right? We need engineers to do everything. So as a scientist, I might want to land at a certain place on Mars, but the engineers are the ones who are going to get us there and make sure that it's safe, right? There's a lot of things. The engineers are sending software. During the Phoenix Mars lander, my husband was the test engineer who actually tested everything that went to the spacecraft before we sent it. Got one shot at it, right? Technical writers are very, very important. We need people to do documentation. So these are people who are actually doing all the documentation. Communications specialists, right? These are all tax-funded dollars. Educators. We need grant writers. It sounds trivial, but that is a highly lucrative career if you want to go into grant writing. We need accountants, artists, mathematicians, animators, machinists. I can't even tell you all these things. And the thing is that no one ever told me that these jobs existed when I was in college. I went, gonna go be a scientist. That's what I'm gonna do, right? It's amazing just the breadth of things that you can do and still work in this type of exploration, or really in lots of different kinds of exploration. So now that I've moved on in my life and I graduated and now I work a lot more in the field of science education, I'm gonna really briefly talk about it for anyone who's interested in maybe making a little career change. I kind of, again, have different pieces of what I do. So I do a lot of social science research around science. So I do these large studies of science literacy and quantitative literacy. So if you ever hear in the news about how scientifically literate is the US population, we do a lot of studies like that. We also look at numerical skills. So we study a lot of students to look at that. I also look at the impact of research experiences. How many of you have done an REU experience? Oh, what a great opportunity. How many of you know what an REU experience is? Okay, can you tell me what an REU is?
It's a summer internship at a different institution where you get to work with current research.
Yep. So it's a summer experience where you get to go to another institution or a NASA center or a national lab, and you get paid to do research. And it is open to all of you, right? As a student, right, lots of people think, oh, can't do the REU. You should apply for them, okay? Even the application process is really interesting, but it's not that you have to have research experience to do an REU, it's that they want you to do experience. And they're opening up more and more opportunities specifically for students at two-year colleges. And so it's something that if you're like, I want to try this out, try it out. Look, this year it's a little late for applications, but I highly, highly, highly suggest doing that. And so a lot of the studies I run studies of both teachers and students, oh goodness, who do these experiences, and I take a look at what does it do for you, right? And the answer is it teaches you a lot about whether this science thing's for you, right? So science is pretty awesome, it's pretty glamorous, but maybe you don't want to sit in front of a computer all day. You want to be a field scientist, or maybe you don't like to get dirty. Those types of things. So it's a pretty important thing. And then I do a lot of studies about where people get information about science. In my other life, I support scientists who do outreach. So I work with a lot with scientists. I teach classes like astrobiology. I may work with in-service teachers and do science outreach. So I do a lot of different things. Right? Just for one slide, I'll show you. This is the other kind of data. It is not nearly as pretty as Mars, right? But these are the kinds of studies that we do. So we did do a study of where students, my students at the University of Arizona, we had a couple thousand of them in the study, get information about science. So you can kind of see, we do large surveys. They get a lot of their information on the internet. No one's surprised. We also do reliability studies where they think about what's a reliable source of information. They still think their teachers are pretty reliable and textbooks and things like that. But what I want to finish with, because I think is actually much more important, I'm going to talk about some of my students. So really quickly, I want to just say, how do we get to the next step, right? And these are the things that I'll talk about. How many of you know where you're going next, what you're doing? I see like half of you have tentative hands. Okay. No one's really boldly telling me where they want to go. So, you can get technical degrees, the internships. I cannot say enough about internships. I have students going out of the University of Arizona with four-year degrees having trouble finding jobs because they're not taking advantage of internship opportunities. When one comes along, I highly, 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 highly suggest taking them. They're very important. Be bold. That'll be my message. Be bold. I have a lot of students who are very timid and are afraid to go for things. You can get a four-year degree, you can go to graduate school. And as I like to say, when you go to graduate school, again in a STEM field, you get paid to go. So it's not the most lucrative job, but it's still a job. But I want to tell you about some of my students to finish. And so hopefully you can see them. So this will give you an idea about some of the other things that they have done. So this is one of the students I've had a wonderful opportunity to work with. Her name is Danielle Adams. Danielle works in anthropology and archaeology. You go, what is that, right? It just so happens that she studied ancient Arabic and now translates ancient astronomy texts. Right? So she was in archaeology, so she was in anthropology and she was in Eastern studies, and then she got this interest in astronomy. And she now is a Space Grant Fellow in Arizona and is translating these ancient Arabic texts. Hopefully, as I like to think, she'll be rewriting your introductory astronomy textbooks. Right? What an incredible thing. But she was able to get a Space Grant Fellowship. So Space Grant Fellowships are NASA fellowships that you can apply for. She was not an astronomer, and she got one, and it pays a stipend for that. This is Emily Joseph. Emily has an undergraduate degree in astronomy and works a lot. She works at the University of Arizona. She does some targeting for the Cassini spacecraft, and gets to do lots of things, again, with a bachelor's degree. And so she gets to work in a technical field. She doesn't have to write grants. she gets to work with the rest of us. And this is one of my recent graduates, Jalan Ali, who is now a math professor at Hillier College. But she and I worked a lot on working with these REU experiences, these industry experiences. Marty was one of my recent PhD graduates. She now is a professor of education, science education. So she came through as a teacher, one of my few teachers, but she now does that. Tenzin, he has just defended his dissertation. He studies Tibetan monks and their understanding of the universe and evolution. And then this is one of my current students right now, Maya, who actually is in public health. So she's going to school for public health, but she gets to work with me for her research assistantship because she asked, right? Because she walked in the door and said, this is kind of cool. I want to work on that, okay? And then my last two students, this is Varanga Pereira. Varanga works in a dual program, so he is a planetary scientist. He studies things inside of asteroids, but he's also working in science education. He'll graduate. And here's James. James is getting an MIS degree and works with us on one of our NASA projects. Right, so we have, like I said, a lot of diversity, but these are all the wonderful students I have the luxury to work with and are doing just fantastic things. And so here's my take-home message, hopefully. There's a lot of jobs in STEM, related to STEM, supporting STEM, right? If you're like, calculus, just not my thing, there are plenty of things you can do if this is exciting to you, right? I like to do, this is one of my soapboxes, that STEM careers are actually very high paying because they're really valuable. They're valuable to our nation, they're valuable to the world, and they're really important to society, right? And so I really consider science and engineering some of the best things you can do however you support them. You can get paid to do them while you're in school. And the last thing I'm going to end with is just to advocate for yourself. And so the biggest thing that I was when I was a student is I was always afraid to walk in and ask about that job. I was too afraid to go work in that lab or take advantage of all the opportunities, right? I just didn't do it. And so that's the only number one thing I can suggest to people if they do move on to larger universities, is to be present and to advocate and to realize that you can do things, you just have to ask, right? And that's how we get a lot of our employees and a lot of our student employees, is they walked in and they were interested. Not that they had the most experience or that they knew anyone. And with that, I will take questions if we have any. Yep. Viking discovered a lot of stuff. It discovered some kind of habitability, but it didn't actually touch water when it was kind of mid-range, yeah. Yeah.
So I guess one of the most impressive things is just how much stuff you do. Maybe it would be nice if you could start to talk to students about how you manage to do all this stuff. Time management.
Whew, yeah. That's a great question. So time management is really important. And I think it comes down to, when I talked about all the things, it comes down to prioritization, right? And so I kind of think about how I'm going to balance my family and how I'm going to balance what I'm doing. But a lot of it comes down to, I don't want to hear this, but I just figure out what are the most important things that have to be done, what are the things I want to do. And so it comes down to just deciding what's important to me. And then I do it. And sometimes, and I give my same advice to my students, what's important may not be getting an A+++, right? It may be doing really well in my courses, but also making time for the rest of my life so I don't burn out. And so I can do stuff like volunteer or spend time with my children and my husband and things like that. But it does come down to just pure discipline. Right, and so we all do things. Lots of people have multiple jobs so they can do things, and so it just comes down to really just making priorities. And I actually use a book, which there's lots of ways to think about that. But I also, I was on the tenure track path path at one time, and that was not for me. And so I had to look inside and say, that's not the kind of job I want to have. And so really making some big decisions there. Yeah.
What made you decide to transition to science education?
For me, I was one of those people, so way back in the day, I used to cut up mice. I was working in developmental mice research, and I decided that I did not enjoy working in a lab, that I really liked to talk to people. And that was what it did for me, is that I felt like that was not my thing, and I just like to be outside in the sunshine. I like to do outdoor stuff, and so that was my transition. But again, right, I was pretty good at it. Wasn't going to be the best, but that was the decision for me. Yeah.
If somebody's interested in becoming a science advocate, how would they get started on that path?
It's a great question. So you can come at doing that different ways. So you can come from a pure science perspective. We have lots of people who will get a master's or a PhD in science and come in from that direction. The most important thing is to get a diversity of experiences. So take a class in education, take a class in communication, or a workshop, and basically make yourself really good at multiple things. So to do the kind of work I do, I have to be really good at science. I have to be really good at understanding how people learn. I have to understand communication. So the best advice is just to really diversify kind of your personal portfolio. Yeah.
So briefly, just explain how you got involved in kind of nonprofit side of the work and how that positively influenced or impacted your career field.
Yeah, so interestingly enough, I got with the Planetary Science Institute because they called me. And they called me because I happened to work in education. And they said, we're a bunch of scientists and we don't know anything about education. Would you be willing to come and work for us? And it has been an amazing thing because I work with scientists all over the world. And because I'm like that weird expert in education, I get to do a lot of things that I suspect I would not get to do. But I very much enjoy, we do a lot of things for the community. And so it's been a really like, going back to like personally rewarding for me. Yeah. Yeah. How do you get involved with that, Mark? So that's when I talk about, that you have to like reach out. So for example, I now have a summer intern because he emailed me and said, I really want to do a video project this summer. Here's something I did. Is that possible? Right? So he reached out. You have a wonderful faculty, and I cannot express how important it is to work with your faculty for opportunities because they know a lot of things. And so that's a really important resource that you have to do that. Because they'll go, oh, I went to graduate school with so-and-so. Let's call them and see. Yeah.
What do you think of Elon Musk's goals to colonize Mars?
Ooh, on tape. So I am very supportive of private exploration of other planets because I think we have a serious problem with federal funding. I think we need to be very careful about the kind of privatization exploration, ethics and things like that. So I'm kind of torn. I think it's a very positive thing as far as R&D pushing forward, but we also need to pause, right? And so there are also people who work in STEM who are ethicists, right? Think about what are the ethical implications of going to other planets. Like that. Yeah. Well, that's a cool question. We have actually a lot of engineering projects going on. So just within planetary science, we do have obviously OSIRIS-REx will be landing. We do a lot of just infrastructure work inside of like rainwater harvesting. We do bioinformatic type work. So it's an incredible place. The other thing we have that's really amazing is a kind of world-class optics department, which is, yeah. Yes, they built pieces of it. Well, it's kind of a collaborative thing, but we do have a lot of optics experts, so we build a lot of cameras. Yeah.
I give a shameless plug before everybody leaves. I'm part of the TRIO STEM program, and this week on April 15th is the deadline for our $10,000 scholarship application. In order to be eligible for the scholarship, you have to apply for the TRIO STEM program, be an eligible STEM major, and be a first-generation college student, meaning that neither
Awesome. Yeah.
About where your rover placements are on Mars, have there been any plans to go to the actual poles themselves, or is that kind of limited by not enough sunlight powering the rover?
Yeah, so it's fairly complex how we choose landing sites, but yeah, it couldn't be a long-term mission because of the solar panels. We're kind of low on our non-solar power options right now. Plutonium's in short supply worldwide. And so really what it comes down to is we have a finite amount of resources, and so interestingly enough, the way we get missions to Mars is we all propose. And we say, here's my idea, and then it goes through a peer review process, and so that's just not high on the list. And so they say, we touched water, we're good. And so there's lots of other priorities that are way far ahead of that, including a sample return. So.
Would one of those priorities be finding a possible landing site for humans on Mars?
Potentially. I mean, we can do a lot of that from orbit because we have such great resolution. Right now, they really are just trying to find the landing sites that they have for Mars 2020 are really trying to say, is there some type of bound up past habitability, past life evidence? So that's what they're looking at. Yeah. Great. Oh, yeah, the last one.
This question's kind of me personal, I think, so I feel kind of selfish asking it. But I've been kind of straddling between astronomy and biology with you, and I saw that you astrobiology, would you say that that would be a good?
Oh yeah, if you like astronomy and biology, astrobiology is a really cool place to be. And I will say that astronomy and biology actually have they don't sound like they have a lot in common, but that's actually my background. So I have a degree in biophysics and I work in astronomy, and so it's a very, very cool thing to do. So, yeah.
So you say they go through planning processes and stuff. So if they were to have people on Mars, what are some of the plans for keeping them there to sustain it, that behavior or whatever?
That's an interesting question. So that's kind of getting out, right? They keep saying it's 20 years away. There's lots of ideas about how we would sustain people on Mars, right? Whether they would build bubbles. So there are actual groups that are out in the desert building bubbles to see could we sustain people in bubbles. Do we take habitat with us? Way extreme is do we terraform the planet? That gets back to the ethics issue about how much we change the planet. And so the answer is it really depends on who you ask. There are a lot of people who are really thinking a lot about this and strategizing. There's no party line. There are just lots of people thinking about it. Yeah. Yeah. Yeah, so that's a great question. So how do you navigate a predominantly male space? And I actually work with a lot of students. And so when I was coming up, right, the advice to me was, don't take it personally, all those things. And so now my advice really is the same thing. It's the same thing I would say for anybody who feels as though they are kind of alone and they feel like they're marginalized, is to advocate for you and to find mentors and advisors and people who really support you, right? And that can be from anywhere. It can be within your department. It can be, there are some wonderful organizations, the Society of Black Physicists, the American Women in Engineering. There are a lot of places that you can become a student member at actually a very low cost to advocate for you using, again, maybe not, if you don't, it can be a faculty member, doesn't even have to be someone who took a class with, but really reaching out. And so the trick is to be bold, and I think that's the hardest thing for a lot of people, because I was that person. I was super shy. I was not going to walk into a single professor's office because that just terrified me. And just really advocating for yourself and finding those people and other students and just being as active as you can. But certainly not to say that this is the way it should be and say, I want more people to be in this major with me and start finding other people. And so that's my best advice, is to be the change that you want to see in that space. So.
Very good job. I'd like everybody to give another round of applause to our speaker today. It was excellent and fascinating. Thank you all for coming, and have fun. Thank you. Bye.